All right, let's dive into something pretty ambitious in physics. It's uh, it's the search for a unified field theory,
Oh, yeah.
which, if you haven't heard of it, is basically a quest to find this like single equation, a theory of everything
Right.
that would explain all the forces and particles
Right.
in the universe.
Yeah.
And we're using excerpts from unified field theory as our guide today.
Absolutely.
So, yeah, where do we even begin? I mean, a theory of everything is.
Well, I think it all begins with the four fundamental forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force.
Yeah, okay, so those are like the building blocks of physics, right? Can you
Exactly.
give us a quick rundown of each one?
Sure. Gravity is probably the one we're most familiar with. Keeps our feet on the ground. It's what governs the motion of planets and stars, that kind of thing.
Right, right.
Electromagnetism is responsible for light, electricity, and magnetism.
Okay.
The strong nuclear force binds protons and neutrons together in the nucleus of an atom. And the weak nuclear force is involved in radioactive decay.
Gotcha. Okay. So four forces, each kind of with its own, domain. But the quest for a unified field theory kind of suggests they're all connected somehow.
Yeah, I mean, there's a growing understanding that these forces aren't completely independent. They're likely different aspects of a single underlying principle.
So it's kind of like these forces were once unified and then they split apart as the universe evolved.
Yeah, that's one of the leading ideas. Physicists believe that in the extremely high energy environment of the early universe, shortly after the Big Bang, all these forces were unified, and then as the universe cooled and expanded, they kind of separated, giving rise to the distinct forces we observe today.
Okay, I can see that. So who were some of the key figures who started piecing this puzzle together?
Well, our journey, it begins with Isaac Newton, back in the 17th century.
Oh, wow. Okay.
His law of universal gravitation was a revolutionary step. It provided a mathematical framework to describe how gravity works.
Right. Newton's apple.
Yeah.
It's just amazing, how something as simple as an apple falling from a tree
Right.
can be connected to these grand motions of planets and stars and everything. So,
Exactly. And then we fast forward to the 19th century. We have James Clerk Maxwell, who unified electricity and magnetism, demonstrating that these two seemingly different forces were actually connected.
wow. Okay.
His equations actually form the basis of our understanding of electromagnetism to this day.
So two forces down, two to go. Did this early success with unification kind of fuel the quest for a more complete theory?
Absolutely. It set the stage for what many consider the golden age of physics, the early 20th century with the arrival of Albert Einstein.
Einstein. Yeah, so
Yeah.
what was his contribution to this grand quest for unification?
Well, Einstein's theories of special and general relativity completely revolutionized our understanding of space, time, and gravity. Okay. Special relativity revealed that space and time are intertwined,
Right.
and general relativity explained gravity as the curvature of space-time caused by mass and energy.
Oh, okay. So instead of a force acting at a distance, now gravity becomes a property of the fabric of space-time itself.
That's right.
Wow.
However, while Einstein's theories worked beautifully on large scales,
Uh-huh.
they faced a pretty significant hurdle, which was the emerging world of quantum mechanics.
Quantum mechanics, that's where things get pretty bizarre.
Indeed. Quantum mechanics governs the behavior of particles at the atomic and subatomic levels, and it introduced profoundly different concepts compared to classical physics.
Okay, so what are some of those key differences?
One of the key principles is that energy exists in these discrete packets called quanta. It's like tiny bundles of energy.
Okay, so it's not smooth and continuous. It's like these tiny little chunks.
Exactly. And it gets even stranger. Quantum mechanics tells us that particles don't have definite properties until they're measured. Instead, their properties exist as probabilities, meaning we can only predict the likelihood of finding a particle in a certain state.
Hold on. So you're saying a particle isn't actually somewhere until we look for it. It's like the act of observation influences reality.
That's the essence of quantum mechanics. It's all about probabilities and the role of the observer. And this is where the clash with general relativity becomes really apparent.
Okay, so we have these two incredibly successful theories. General relativity for the large scale,
Mm.
quantum mechanics for the small scale. But they seem to be speaking different languages.
Exactly. General relativity describes gravity as this smooth curvature of space-time,
Right.
while quantum mechanics describes a world of discrete quanta and probabilistic behavior.
Right.
And reconciling those two seemingly contradictory frameworks, I mean, that's the central challenge in the quest for unified field theory.
So did Einstein just give up then? I mean, he revolutionized our understanding of gravity, but then this quantum stuff comes along. Did he just throw his hands up?
Not at all. He spent a significant portion of his later years trying to unify gravity with electromagnetism, but he ultimately was unsuccessful.
Wow, it's I don't know. I find that kind of humbling that even Einstein, this genius,
Right.
struggled with this problem. Shows you how difficult it is, huh?
It does, but his efforts and his struggles paved the way for future generations of physicists to continue this pursuit.
So where did the quest go from there? Did anyone else make progress after Einstein's efforts?
There was a major breakthrough in the 1960s
Uh,
with the development of what's called the electroweak theory.
okay.
This theory was developed by Sheldon Glashow, Abdus Salam, and Steven Weinberg,
Okay.
and they successfully unified the electromagnetic and weak forces.
Two more down. Are we halfway to a theory of everything then?
Not quite. Unifying gravity with the quantum world, that remains the ultimate goal. But the success of the electroweak theory was a significant step. It showed that unification is actually possible, and it gave hope for further progress.
So the electroweak theory kind of combined these two forces into one. Where did that leave the quest for a unified theory?
Well, it provided a critical piece of what became known as the standard model of particle physics.
Okay.
This model incorporates the electroweak theory and what's called quantum chromodynamics, QCD, which describes the strong force.
Okay, so we got the standard model bringing together three of the four. Electromagnetism, the weak force, strong force, but it still doesn't include gravity.
That's right. The standard model, while incredibly successful in explaining a vast array of phenomena, has its limitations.
Yeah.
And it doesn't incorporate gravity, and that's a major piece of the puzzle that's still missing.
Okay, so what are some of the more modern approaches then that are trying to kind of fill that gap and bring gravity into this quantum world?
There are a few contending theories, with string theory being one of the most well-known, and perhaps the most mind-bending.
String theory. Yeah. That's where things get really interesting, huh?
Hmm.
What is it about string theory that makes it so compelling and so challenging?
Well, string theory proposes a very radical idea.
Okay.
It says that the fundamental building blocks of the universe aren't point-like particles.
Right.
They're tiny, vibrating
Or
strings.
strings.
Think of it like the strings on a guitar, where different vibrations produce different musical notes.
Uh-huh.
So in string theory, different vibrations of these strings would give rise to different particles and forces.
Okay, so instead of particles, we have these tiny little vibrating strings.
Hmm.
And the way they vibrate determines what they are.
Exactly.
Okay. But I've heard that string theory requires these extra dimensions to work.
Hmm.
How does that fit into the picture?
That's right. To make the math of string theory consistent, it actually requires more spatial dimensions than the three we experience in our everyday lives. Length, width, and height.
Extra dimensions. So where would those extra dimensions be? I mean, are they like hiding somewhere?
String theory suggests that these extra dimensions are what we call curled up or compactified to these incredibly small scales, billions of times smaller than an atom, which is why we don't perceive them directly.
Okay, so we might be living on a giant cosmic string.
Right.
And there could be these other universes out there hidden in these curled up dimensions. It's starting to sound like science fiction.
It does push the boundaries of our imagination, but it's important to remember that that string theory is still a theoretical framework, and it hasn't been experimentally confirmed.
So is string theory the only game in town? Or are there other approaches to unifying gravity with the other forces?
There are other approaches. One of the most prominent ones is loop quantum gravity,
Okay.
which takes a different approach to quantizing gravity.
What's the main idea behind that one? How does it differ from string theory?
Well, loop quantum gravity focuses on quantizing space-time itself. It suggests that at the what's called the Planck scale, the smallest possible scale,
Mm-hmm.
space-time isn't smooth and continuous, but it's made up of these discrete, interconnected loops.
Loops like
Think of it like a fabric woven from these tiny loops of thread.
okay, so instead of smooth space-time, we have this network of interconnected loops.
Yeah.
Okay. Does one approach seem more promising than the other at this point?
It's still too early to say. Both string theory and loop quantum gravity are active areas of research, and they each have their own strengths and weaknesses.
I'm kind of sensing a theme here.
Yeah.
Even with these cutting-edge theories, a complete unified field theory, this theory of everything, still feels pretty far off. Is that a fair assessment?
It is. The quest for a unified theory is it's an ongoing journey full of challenges and uncertainties,
Yeah.
but it's also filled with the potential for incredible breakthroughs and insights.
I guess that's the nature of science, huh? It's not always about finding definitive answers, but just continually refining our understanding.
Here's the
Stacking
speaker.
these
Yeah.
deeper questions, pushing the boundaries of what we know.
Absolutely.
Okay, before we dive into the deeper implications and the future of this quest, let's just take a minute to recap what we've covered so far.
Okay.
We've gone from Newton's law of gravitation to Einstein's theories of relativity, then to quantum mechanics, string theory, and loop quantum gravity, all in pursuit of this elusive unified field theory. So, what are some of the key takeaways you'd like to emphasize?
Well, I think what's remarkable is that this quest for unified theory isn't just about finding a single equation, as elegant as that would be.
Right.
It's about deepening our understanding at the very fabric of reality,
Yeah.
questioning our assumptions, and really pushing the boundaries of human knowledge.
It's about that, that human desire
Yeah.
to
Hmm.
to understand our place in the universe, to make sense of, the universe and how we fit into this grand scheme.
Exactly. And in the process, we've had to, uh, confront some pretty profound questions about the nature of space, time, matter, and energy.
Yeah.
I mean, think about it. We've uncovered these mind-boggling concepts like the curvature of space-time, the probabilistic nature of reality, the potential for extra dimensions, the possibility of a multiverse. It's incredible.
It really is.
And each step in this journey has challenged our intuition and just expanded our understanding of what's possible.
And the journey is far from over, right?
Absolutely. So join us as we continue this deep dive into the quest for a unified field theory. And we'll explore some of the profound implications of this ongoing scientific adventure. It's amazing, isn't it, this search? It isn't just about finding one equation. It's like this journey
Right.
that's making us think about these deep philosophical questions about reality itself.
Yeah, it's true. I mean, we've moved on from thinking about gravity as like this force acting at a distance to it
Wow.
being the curvature of space-time. And then quantum mechanics comes along.
Right.
And it's like, wait a minute, reality might be probabilistic. Things don't even have definite properties until we observe them.
Yeah.
And what
It really is almost as if the universe is playing dice with how we see reality.
exactly? And it makes me think, what does all of this mean for how we understand the scientific method? Like, if reality is, at its core, uncertain at this quantum level,
Right.
does that mean there's a limit to what we can know, what we can predict?
That's a question that philosophers of science have been debating for decades now.
Really?
This probabilistic nature of quantum mechanics, it challenges that classical view of science where we're trying to find these deterministic laws that govern the universe.
Right.
It's like, well, at least at this quantum level, we might have to accept some uncertainty. There's this fuzziness around the edges of reality.
So are you saying we have to rethink what scientific objectivity even means?
It definitely raises important questions about the role of the observer in quantum mechanics. Does observing something create reality, or is it just revealing something that was already there?
Right.
These aren't easy questions to answer, and they really highlight the philosophical side
Yeah.
of this quest to understand the universe, how it works.
It's like the search for a unified theory isn't just physics, it's about us.
Yeah.
And how we see things.
Exactly. It makes us rethink our ideas about reality,
Yeah.
about what we can know and how we even know it.
Yeah. Okay, but honestly, why should the average person even care about a unified field theory? I mean, it's fascinating, don't get me wrong.
Right.
But does it have any impact on, everyday life?
That's a good question.
Yeah.
I mean, it can seem abstract, this whole thing, far removed from our lives, right?
Yeah.
But historically, when we've made progress in fundamental physics, that's led to some pretty big technological changes for society.
Oh, okay. Can you give me, like, an example?
Sure, think about Maxwell's equations, unified electricity and magnetism, right? That led to radio, television, all the electronics we use. Or Einstein's theory of relativity seemed totally theoretical at the time,
Right.
but now it's essential for things like GPS.
Oh, wow. That's true.
So even if we can't see how a unified theory would be useful now, history tells us it could lead to things we can't even imagine.
Okay. Yeah. It's like we're at the start of something big,
Right.
but we just can't see what's coming next.
Yeah, exactly. I mean, unifying gravity with these other forces, who knows? Maybe new ways to understand energy,
Right.
matter, even space and time, maybe breakthroughs in energy, materials,
Yeah.
communication, transportation.
Yeah.
Who knows?
It's exciting, but let's be real for a second. We've talked about these big implications, the tech that could come out of it.
Yeah.
What's standing in the way? What are the big obstacles?
One of the biggest, it's just plain hard to combine general relativity, the large scale stuff,
Yeah.
with quantum mechanics, the microscopic world.
Yeah.
They work on such different scales
Right.
and with principles that don't seem to fit together.
Right. It's like putting a square peg in a round hole or something.
Exactly. And to really study where gravity and quantum mechanics meet,
Yeah.
we need experiments with way more energy than we can make now.
So bigger, better particle accelerators, like the Large Hadron Collider, but even bigger.
That's one way.
Okay.
The LHC has been amazing for particle physics.
Yeah.
But to get into quantum gravity,
Yeah.
we probably need something way more powerful.
What about the theory side? Any roadblocks there?
Oh, yeah, definitely. Like with string theory, it's really hard to test the predictions.
Okay.
You need a ton of energy to see how strings behave. We just can't do that yet.
So even if the math is beautiful, we need to see it in reality, huh?
Exactly. And then with loop quantum gravity, the problem is coming up with the math that fully describes quantum space-time.
So we need both, right?
Yeah,
Experiments and theory both have to advance.
absolutely. It takes both.
What excites you most about this quest for a unified field theory?
For me, it's the possibility of these huge shifts in how we understand the universe.
Yeah.
Like, think about when Copernicus said the Earth wasn't the center of everything, or discovering quantum mechanics. A unified theory could be that big.
Wow.
It could change how we think about space, time, matter, energy, everything.
Sounds like we'd have a whole new way to talk about reality.
Exactly. A unified theory wouldn't just be equations, it would be a new way to see the universe.
That's pretty inspiring. So what's next? Where do we go from here?
The search goes on in many ways.
Yeah.
Experimentally, we're building bigger accelerators,
Uh-huh.
making better detectors to study things like gravitational waves, looking at the universe more closely with telescopes, all that.
So we're looking inward at the tiniest stuff
Right.
and outward at the vast universe all at the same time.
Exactly. And for theory, there's research on string theory,
Yeah.
loop quantum gravity, other ideas too. Plus, trying to develop new math that can bridge the gap between relativity and quantum mechanics.
It sounds like an exciting time to be a physicist.
It is.
But I have to ask, if we do find this theory of everything,
Yeah.
is that it? Is physics done then?
Physicists debate that all the time.
Really?
Some say a unified theory would be the ultimate thing, the final answer,
Right.
but others think it would just be a new beginning.
Okay.
It would raise even deeper questions, new mysteries.
It's like you climb one mountain,
Yeah.
and then you see a whole range of new mountains in the distance.
Precisely. Science never stops. It's about pushing what we know and going into the unknown. A unified theory, even if we find it, it wouldn't be the end of physics, just a new start.
It feels like we've been on this intellectual journey
Yeah.
with this deep dive. We've looked at the four fundamental forces,
Right.
followed how we understand gravity from Newton to Einstein,
Right.
and even dipped our toes into quantum mechanics, string theory,
Yeah.
loop quantum gravity. It's a lot to take in.
It is a lot. And we're just scratching the surface
Yeah.
of this huge complex field.
Through all this quest for unified field theory, I keep thinking, what would it even mean for us
Yeah.
if we actually found it? Would physics be over then, like some people say? Or would it be the start of something even bigger?
That's a tough one to answer.
Yeah.
On the one hand, a unified theory would be huge. Centuries of science led to that.
It would show how powerful human reason is,
Exactly. It would mean we figured out the universe's deepest secrets.
It'd be like the Rosetta Stone for the cosmos,
Hmm.
unlocking how it all works.
Exactly. But, like we talked about before, it might not be the last word. It could open up, whole new questions, things we haven't even thought of yet.
Oh, wow.
Deeper levels of reality beyond what we understand now.
So not the end of physics,
Right.
but a super exciting new phase.
Exactly. Imagine climbing a mountain.
Yeah.
And when you get to the top,
Yes.
there's a whole mountain range behind it, waiting.
Wow. Yeah. Think of the
Ah.
possibilities. If we knew how reality really works, it could change energy, space travel, maybe even how we think about consciousness.
Yeah, the impact could be huge.
Right.
We can't know what it would look like, but for sure it'd be a future where we understand the universe
Right.
and our place in it much better than we do now.
It's uh it's worth working towards,
Absolutely.
even if it's hard and we don't know what we'll find.
The search for knowledge,
Yeah.
trying to understand the universe, that's one of the best things about being human.
Yeah.
Even if we don't get that complete unified theory, the journey itself is what matters.
Yeah, I like that.
Makes us think bigger.
Well, I think that's a great place to wrap up our deep dive into this search for unified field theory.
Yeah, it's been a fascinating one.
We've gone from gravity, something we all know,
Right.
to string theory and even weirder stuff.
Yeah.
We've asked about reality, what we can even know.
It's a lot.
And we've seen that maybe in the future we'll have a much deeper understanding of the universe.
And as we finish up, here's something to think about.
Okay.
What would a world with a unified theory look like? How would it change how we see ourselves, our place in the cosmos, what we could do in the future?
It's a big question.
It is one worth thinking about as we keep exploring.
Thanks for joining us on this deep dive.
Yeah, thanks everyone.
We hope it made you curious and maybe inspired you to keep learning about science and the universe we live in.
Keep asking the big questions, never stop searching for knowledge.
Yeah, there's so much out there.
The universe is full of amazing things waiting to be discovered.